Okay, so good morning. We're going to make a video, show you the type 2 improper integrals. So let's get started. So if I give you, we'll just start off with a quick example here just to give you an idea of what's going on. Okay, so if you just look at that problem, if you just look at that integral, you might think there's nothing to it. Like, it looks pretty benign, looks normal. Might think, oh, let's just go ahead and do this. But if you look real carefully, that function has a vertical asymptote at 2, and it actually would look something like this. Okay? So when I integrate from 0 to 4, I'm integrating over that vertical asymptote. That's what defines this as a type 2, or what I call a type 2. We're integrating across the vertical asymptote. Okay? So the way we do this is exactly the same way we do the type 1s. Since I'm going to 4 over here, I need to actually compute 2 limits. So we'll set this up like the limit as b goes to 2 from 0 to b. And I'm going to actually put from the left there. If you don't put that, I'm not going to freak out. And then I'm going to add to this, I'm going to add to that the limit as b goes to 2 from the right. And then we just go ahead and compute them just like we did the ones yesterday. Okay? So we find the antiderivative. So this is negative 1 over x minus 2. We'll evaluate that from 0 to b. And then over here, we'll just do the same thing. Evaluate that from b to 4. And now we'll go ahead and calculate this, or, well, evaluate it first, then calculate the limit. So that's going to be negative 1 over b minus 2 minus negative 1 over 0 minus 2 plus, and then we'll go ahead and write limit as b goes to 2 from the right, negative 1 over 4 minus 2 minus negative 1 over b minus 2. Okay, so here we are. Now we're going to compute this limit. So as b goes to 2, what happens to this right here? Well, as b goes to 2, this is 1 over 0. This is approaching infinity. And you're done at that point. As soon as you get an infinity when you're doing one of these computations, you're done. Sometimes you might get an infinity and then a negative infinity and think that those cancel each other out, but that's not the case. Because remember, infinity is not a number. Infinity minus infinity is not necessarily 0. So you're done. So this integral here diverges. Okay? Let's look at another example here. Pre-worked out a couple of these. So how about 0 to 4 of 1 over x minus 1 dx. So again, you have to recognize that this is improper, that this is a type 2. You got to check that denominator and say, hey, is 0 to 4, is that thing undefined between 0 and 4? And it is at x equals 1. So we'll do the limit as b goes to 1 from the left. You go from 0 to b of 1 over x minus 1. And then we'll add to that the limit as b goes to 1 from the right, and then go from b to 4. So we're basically just breaking up that interval into two pieces. Okay? And now we'll go ahead and anti-differentiate, just like we did before. Anti-differentiate on this one. Now it's going to be the same antiderivative, right? I mean, so now I've got the limit as b goes to 1 from the left of the natural log of absolute value of b minus 1 minus the natural log of negative 1 absolute value. I plug in 0, and then I got the limit as b goes to 1 from the right of the natural log of 4 minus 1, which is 3, minus the natural log of b minus 1. Okay, so now we're going to go ahead and compute this limit. What happens to this right here as b goes to 1? Well, as b goes to 1, I have the natural log of 0, which is negative infinity. So immediately we can say that this type 2 improper integral diverges. Okay? So the way you actually end up computing them is the exact same. It's just how you set them up initially. You go ahead and you break it up if you need to, and change to b just like we did before. But then you go through and compute these limits just like we did before. Instead of computing a limit as b goes to infinity, you're computing a limit as b goes to 2 or 7 or 3 or whatever. All right, now let's take a look at something else, because there's something else I was going to show you in this video today that's sort of an extension of some of this. Well, yeah, an extension, I guess. All right, let's see. I could have paused that. I actually am running a different software. I could have paused while I erased. So sorry that you had to sit through that. So what I want to talk about now is what happens if we compare improper integrals. And we're specifically going to be working with type 1s here, not the type 2s. What happens if we compare improper integrals? What do I mean by that? Well, let me give you an example. Let's just start off with this cute, simple-looking improper integral, okay? So why don't you pause the video, take 2 seconds, 2 minutes, pause the video, and tell me if that converges or diverges, okay? I'll come back with the answer in a second, but it's a pretty simple one to do. Go ahead and compute it and tell me if it converges or diverges. Okay, so pause the video. I'll give you a second. I'm going to have a cup of coffee. I'm going to go back and fill up my coffee while you're pausing. All right, so I bet hopefully you've paused and you've computed that and you found that that integral right there converges. Okay? So this converges. All right? But now I want you to look at this integral. Okay? Look at that integral. And I want you to pay very close attention to the integrand, the function that you're integrating. Okay? How does this compare to that one right there? All right? Well, it looks exactly the same, except there's a plus 6 in the denominator. But let's think for a second what that plus 6 in the denominator does to this function compared to this function. If you really think about it, what happens if you're comparing two fractions where the numerator is the same but the denominator is bigger? The one with the bigger denominator is actually smaller. So what that means then is that this function right here is always smaller than that function right there. And if I just showed that this converges, this guy right here is going to have to converge because it's smaller than something that converges. Think about that. If you're smaller than something that is finite, you have to be finite, right? I mean, think about that. So we're going to say, since this right here is less than this right here, and how do we know it's less than? Because the function is always smaller. If I were to graph this function and I were to graph this function, this one would always be below that one. Okay? Since this one is less than this, and this guy converges, that means this guy converges. Okay, and we call this kind of the comparison test. If I can show that this function's less than one that I know converges, it's pretty easy to do. Now, obviously, the hard part about this, or the work involved, is showing that this converges. But in a minute or in about 4 minutes, I'm going to show you a shortcut on how you can just look at that and tell me that it converges. Okay, well, how does this comparison thing work with diverges? Let's think for a second and just develop this out loud before we look at an example. If something diverges, if I show something is less than something that's infinite, does that mean that it's finite? Think about that. If I show you that something is less than something that's infinite, does that mean the thing I'm comparing is finite? The answer to that is no. And it's a real simple thing, because both of them could be infinite. And if you think about this, here's a very easy example to sort of put your head around. The set of integers is an infinite set, right? The set of integers is an infinite set. Well, the set of real numbers is also an infinite set. And there are fewer integers than there are real numbers. But they're both infinite sets. Okay. Now on the flip side, if I can show that a set or an integral or something is greater than something that's infinite, then it must be infinite. If I can show you're bigger than something that's infinite, then you must be infinite. So that's how we're going to use this same idea. So let's look at another example here. So take a look at this guy. 1 over the square root of x. Okay, pause for 10 seconds and tell me what that one does. Well, you're probably going to know, since if you were following along, you're probably going to know what that one does. But go ahead and pause for 10 seconds and calculate what that one does. Okay, so you should have gotten that this one diverges. Okay. That diverges. Woohoo! All right, now, but I want you to compare that with this integral. 1 over the square root of x minus 6. Okay? Now, if you think about this, 1 over the square root of x minus 6 compared to 1 over square root of x. Okay? Again, we're looking at two fractions here with the same numerator and different denominators. This denominator is always less than that denominator for all values of x. So what happens if you're comparing two fractions and the one fraction has a smaller denominator? It's actually a larger fraction, right? If I were to graph this function right here, and I were to graph this function right here, this guy right here would be higher than this one for all values of x. Okay? okay, well, what does that mean? It means that if this area is infinite, this area is going to have to be infinite as well because it's bigger than this one. So same idea. Since 1 over the square root of x minus 6 from 1 to infinity is greater than 1 over the square root of x, and 1 over the square root of x diverges, this other guy diverges as well. So how can we sort of summarize this idea of comparison? Okay, it's pretty simple. If you have a known integral that converges, if you can show that an unknown integral is less than that converging integral, the unknown one converges. And the flip side of that, if you have a known integral that diverges, if you can show that an unknown integral is bigger than a diverger, then it diverges. Okay? So let's put that in words. We'll write it right here. So if integral, let's say an unknown integral, if an unknown integral is less than a known converger, the unknown converges. And on the flip side, if an unknown integral is less than a known diverger, nope, sorry, not less, greater than, sorry, I was rewriting that and just copying it again. If an unknown integral is greater than a known diverger, the unknown diverges. Okay? And that's what we did here. We showed this integral was less than this one, which we knew converged, so he converged. This one here we showed was greater than this one here that diverged, so he diverged. Okay? So that's what we call like the comparison test or the comparison rule. We'll actually look at this comparison test more when we start talking about infinite series in the spring. Now let's back up a second, because these two integrals that I gave you and said take 10 seconds to tell me if they converge or diverge, you probably work those out by hand. Okay? Well, I'm going to give you a quick little trick that I'm not going to prove just for the sake of to keep the video shorter, but I'm going to give you a quick little trick on how you can just look at a lot of integrals and just tell me if they converge or diverge. Okay? So I'm going to erase. Too lazy to go over there and walk to hit the pause button, so you're just going to have to watch me erase. I could tell a joke or something while I'm erasing. I don't know if you guys saw the news that Tiger Woods was in a really bad car accident. Unbelievable that he survived that. I mean, fortunate that he survived it, but it just looked horrible. So, all right. So here we go. Here's our quick little check to determine we can just look at an integral, certain types of integrals, and determine if they converge or not. And those are integrals that are of the form 1 over x to a power. And we would just say from a to infinity. I like putting 1 there, but you'll see other numbers there. Okay, but 1 over x to a power. Okay, like 1 over x squared, 1 over x cubed. Let me just run through some examples of what these look like. 1 over x squared. 1 over radical x. Because what would the power be here for x? It would be 1/2, right? 1 over x to the pi. The power would be pi there, right? Okay, these are affectionately referred to as p-integrals. Wow. Okay, they're p-integrals. All right. Simple rule. A p-integral, if it's of this form, it converges if, anybody know? Now I'm asking you as if you're going to answer me. I'll bet some of you know the answer to this because you've sort of seen what's happened, or you know kind of what the answer is, because you've seen the examples that we've done and you've done your homework and you sort of you're in tune with what's going on. But these converge if p is greater than 1. So any power of x that's bigger than 1 converges. Okay? And they diverge if p is less than or equal to 1. Okay? So let's real quickly run through these babies and determine. What does this one do? What's the power for x? 2. That converges. P equals 2. What's this one do? That diverges. P equals 1/2. What's this one do? Well, pi is greater than 1, so that converges. P is greater than 1. Well, P equals pi, which is greater than 1. Okay? So those are p-integrals. That's why when I gave you those first two problems when we were doing this comparison, when I gave you the things that we were comparing to, that's how I was able to do those so fast. They're p-integrals. So that's it for the video today. I hope you enjoy your Wednesday. It's supposed to be 50 degrees today. Hopefully you can get outside and pick up some sun. I'm going to put some other problems on the Google for you to add, to work on. There won't be any problems directly addressing p-integrals. If you want to use the p-integral rule to show converging or diverging, you're certainly welcome to do that, but there aren't any specific problems. In fact, our book doesn't even teach p-integrals. So most of these problems that I'm going to give you today are going to just be dealing with type 2. There's about 5 or 6 of them that I'm going to give you. So that's all. Have a good day.